Good morning. Before we get started on these questions, there were some questions in the first class on the difference between a small and a large base. And it does just come down to size. So small bases are going to be things like NaH, whoops, which is literally just a hydride. NaOH, NaNH2, probably the biggest things you're going to start to see is maybe ethoxide or the amine version of that, ethylamine. Large bases are literally what it sounds like. So like diisopropylamine, LDA is one you guys are going to see a lot. Terbutoxide, the isopropyl version of that would also be considered a large base. Pyridine's kind of on the edge, but you could throw it in there. And another one you might see is called DBU, or sorry, DBX. DBU, that's what it said. Literally bases that are very large. So anything bigger than an alpha group, I would throw into that large versus small, or small, yeah, large versus small category. All right, I'm gonna give you guys a few minutes to write this down, and then I'm gonna throw those problems back up. All right, so I'm gonna give you guys about 5 minutes to go through these, and then we will get started on some new reactions. All right, so we are going to first take a proton. We can pull off one of these beta protons. Symmetrical, doesn't matter which one, so water can pull off one of these. And we are going to make an enol. So an enol is the neutral adduct. You have this proton here on the oxygen. It's not negatively charged versus the next one. So LDA, as we said, was a large base. It can pull off one of the protons. It's going to be selective for the less substituted center because it's a large base. So it'll pull off one of these secondary protons here. We're going to generate, in this case, an enolate. Which is the negatively charged version of it, like so. NaOH is going to be selective for our more substituted center. It's a small base. So same concept. If we add in HBr, we can, so let's take just the adduct. So I'll just draw that same concept as we were doing over there. This can attack a Br here. We are going to brominate. In this case, doesn't matter whether it's both sides are the same. So we're going to add a Br to this beta position. Oops, not aromatic. Beta position like so. LDA is going to be selective for our less substituted center. So in this case, we are going to brominate on our left side, which is conveniently our less substituted center. And then NaOH is going to selectively pull off the more substituted position to give us that Br on our more substituted position. All right, if I block one of the ends of this and add an NaOH, so making it into a terbutyl. There's now no protons over here. I've got 3 protons over here. If I add in NaOH Br2, I'm going to brominate. If I added an excess, I'm gonna end up tribrominating. And this CBF3 group I just made, or sorry, BR3, it's a really good leaving group. And this is really similar to an acid chloride. So if I was to throw in H3O+, I can change this to a carboxylic acid. So as a review, if I just have a long chain, if I throw in BR2, NaOH BR2, I have a primary and secondary position, be selected for the secondary. Just gonna bring it over here like normal. If I block it by turning that into a tert butyl and add an NaOH in excess, sorry, Br in excess, NaOH is catalytic. I can tribrominate. And then if I do the same thing with water at the end, or I guess H0+, because I got to balance out the NaOH, I can make the carboxylic acid. All right, so that's the end of this haloform reaction. I'm going to talk about the aldol reaction and condensation today. Did I meet or remove a carbon in the last product? Yes, you literally burn off this carbon and make a carboxylic acid, unless I removed it somewhere else. Okay, so as kind of a review of probably OChem 1, if you have a ketone, this is going to have a pKa for this proton of around 19. An aldehyde our beta proton here is going to have a pKa of around 17. If we have a diester, which we're not going to talk about as much today, but we will in the future, these protons here have a pKa of around 13. If I remove one of the esters, so I keep the carbonyl, so ketoester, This is gonna have a pKa of around 11. Diketone. Gonna have pKa around 9. I didn't draw this blue. This is going to be important because if we have something where we have both a ketone and an aldehyde in solution, for today, later on, we'll do these other ones. So ketone plus aldehyde, and let's say we throw in NaOH. Because this is a pKa of around 19, this one is around 17. We are going to selectively deprotonate just the aldehyde. And get just that enolate. All right, but before that, let's talk about just the regular reaction, which is called the aldol addition. Aldol addition. This is mechanism 21.4. We are going to take, in this case, just an aldehyde. We'll start with just that. Throw in NaOH. We can pull off this alpha proton here. Make an enolate. This can then react with another equivalent of itself. So another version of our aldehyde here. We're going to do a cross reaction where these electrons are going to come down. Our double bond is going to come attack our aldehyde, kick up its electrons. So we started with 2 carbons here, attacking 2 more carbons. We end up with a 4-carbon chain. We kicked up these, so this is an O- now. And then from here, we made water in the first step so we can pull off that proton. And we're going to get our product. All right, so just to rewrite that real quick, we're going to take an aldehyde plus itself. Going to make 1 enolate. When we throw in NaOH, it's going to create this aldol product here. And then what we can do from this point is if we add in heat, and I'll go through this mechanism in a second, we're going to do a condensation where we're going to form a double bond that is conjugated to this carbonyl here. So we're going to end up eliminating water and forming this. You're always going to end up forming the double bond next to your carbonyl. You're never going to get this one because this wouldn't be conjugated. Okay, so this is what's called the aldol condensation. Should be mechanism 21.6. So our first part of it's exactly the same. We're going to take an aldehyde, throw in NaOH. This time we're in heat. First step, we're going to pick up the proton, make our enolate. This can attack another version of our aldehyde. Pick up a proton and generate our addition product. So this is the exact same thing we just did. From here, what we're going to have happen, we're going to do a bit of a proton shuffle. So in heat, you can do this all in one step, which is nice. We just made NOH minus. We are going to pick up this proton, eliminate water. The water is going to grab the other proton from our NaOH. It's a bit of a cyclization. So we're grabbing this proton, we're losing this proton, and we're going to make our condensation product plus another OH minus. All right, let's do one more of these. For the last step, it should be OH minus because you made water here, but then you picked up this H here and made it back into OH minus. Do a slightly more complicated one. I'm going to draw out both equivalents. So we're going to make this enolate here. It can do an attack. We're going to form a bond between this position here and our other ketone or other aldehyde. We'll protonate. And then throwing in heat lets us do our condensation. To get our product. All right, so let's make it a little bit more complicated and do what's called a cross aldol. All right, if I have two different aldehydes here, I can get 4 products from this reaction. So what'll happen first is I'm going to throw in NaOH. And I can get 2, well, I get the same enolate for both of these. So I'll make an enolate which looks like this. Nope. Same thing over here. And then this will either react with itself, so we can have this make initially our alcohol, and then in heat give us our condensation product. Or it can react with the other aldehyde in solution. So in this case, 2 different products, depending on whether or not you're attacking this, which just has like an ethyl, versus the propyl here, you could add an extra carbon at the end of this. Okay, we'll draw the purple. So those are the right 2 products, or sorry, left 2 products, I guess. we can also make an enolate out of this one on the right here. So if I deprotonate that, I'm going to make an enolate. I'm going to draw it twice. It can either react with an equivalent of our ethylaldehyde, which is going to make a different alcohol, which can lead to a product, condensation product. I want to be red. Ooh, wow, that was a mess. Draw that over here. Or it can interact with itself. Which can again eliminate or condense to form another product. I'll give you guys a second to get caught up. So if you look at these, you can see your carbon skeleton. You have these two carbons from your original molecule, these two carbons from the one it attacked. These two are from the original. These two in the blue are from the ones you attacked. Blue, red, blue, blue here. And I'll do another one of these that'll be a little bit more. Oh no, there's no major product. These are all major products. There's not going to be a way to determine which one is more likely to form. All right. Make it a little bit different just to get us used to it. Let's do this here. So NaOH heat. Oh, the heat. There we go. So I didn't draw them in two different colors, whatever. If I draw this reacting with itself, it's going to look going to have one equivalent. It's going to attack another version of itself. No, I want to draw in red because it's not changing. We originally had an alcohol here, but then we condensed it to a double bond. If it attacks our other aldehyde, it's going to make a bond to it. We originally had an alcohol, end up with a double bond there. Let's start with this. skeleton, it will attack from this position to give us this, and then we can do it to itself, which is going to be quite large and give us something like this. If you want to think of it as, instead of there being an H here, this is now the bond that's attached to your beta position. That's another way to think of it. Okay. So let's go back to a page we talked about at the beginning, which was this pKa chart here. So if I have both a ketone and an aldehyde in solution, I'm going to do this deprotonating selectively for an aldehyde, because that is slightly more acidic. So if I try to do a similar reaction, here, I'm going to have some selectivity. So I can make this aldehyde enolate but I'm not actually going to make my ketone enolate because it's less acidic. It's going to selectively just deprotonate this aldehyde here. And from this point, I can get two different products. So this can either interact with itself, which would give me this aldol condensation, or if it interacts with the ketone. We haven't really done many ketones, so I'll draw this one out. Would originally give us this alcohol, which we could condense to our product. Before you add the heat, is there a methyl next to the alcohol? Yeah, sorry, this should be, that doesn't look great, does it? This kind of looks like it's a weird carbonyl or something like that. So it should be two methyls here and an OH. Okay, so ketones we said are a little less selective. You can do a ketone aldehyde with itself. Oh, someone asked, why are there two methyls? Because you have it's a ketone instead of an aldehyde. So normally we would have one of these would be an H typically. Like if I draw out what we did over here, we don't normally think about this H here because we're dealing with an aldehyde. We have a ketone, it's 2 methyl groups, which means we need both of those methyl groups to be there, as opposed to the aldehyde where you have a methyl and a proton. Okay, so let's do just a ketone aldol first. NaOH and heat here. We're going to make our normal enolate. We attack another version of itself. We can make our alcohol and then do a condensation. Like normal. If we want to be selective, so let's say we actually want to do this to a aldehyde, we want to have the ketone attack the aldehyde. One thing we can do is we can separate the steps. So if I add in NaOH by itself, that is going to selectively deprotonate this as enolate, and then I add in my aldehyde. This will let me do it where I actually have my ketone attack, even though it is the less acidic version. But because we're doing ketones, this is going to complicate things a little bit. So let's take these two reactions and talk about why they're different. I was watching the chat. I already did that one. Okay. So we're going back to our small base versus large base rule. NaOH is a small base, which means that we're going to make an enolate that looks like this here versus our one on the bottom where we have LDA. Our large base is going to give us a different enolate. So these are going to lead to different products. This can attack our aldehyde here. To give us this aldol condensation reaction versus the one on the bottom here, because we deprotonate in a different position, we're going to get a different product. So we made our enolate on this side, it came and attacked, and then this methyl group is on the left versus in this one where it's basically shifted over to down here because we flipped our molecule for where we're generating that. Okay, I'm going to stop here for today. On Wednesday, we're going to do more of these and then do a few more reactions, which are similar, a little less complicated, and talk about some more of chapter 21. So I will see you guys on Wednesday.